think we're going to get started. What we were planning to do is come back and have a few questions, if anyone had any, for our morning speakers. Though I did see that the three speakers were kind of buttonholed and asked questions throughout most of the break. So I don't know, it sounds like there was some discussion that happened. But does anyone have any quick questions or, any burning questions? I'm not sure Barbara's back yet, but yeah, Chris.
Thanks, Chris Klein, Southwest Research. So this is for Jeff. I'm really interested in the sequence from CO2 to methane. It looks like methanol is the bottleneck. And I'm wondering, why is that? Have you tried to do an experiment starting with methanol? And does it make methane? Like, do you need to build up enough methanol before methane can form? Or is there a mechanistic problem in reducing methanol?
So glad you asked that question. One of the things that I forgot to mention during the talk is, so you're absolutely right. We see the accumulation of methanol in solution, which actually reaches thermodynamic equilibrium with the CO2 and the hydrogen. And the slow step in the process is the reduction of methanol to methane. And if you actually, the slide that I showed, what we actually see is the rate of methane production increases with time as the methanol accumulates in solution. I have done an experiment actually where we started with methanol and we make a whole bunch of, you make methane, you make carbon monoxide, a whole bunch of other stuff.
Any other questions? Sorry. Oh.
Yeah. Years of softball. Okay, so I had a question for Barbara. Is she back? No. Okay, I have a question for the room. Why? So Barbara started her talk saying that the abiotic, basically the background, the filter, whatever you want to call it, but to me, like looking at the system and trying to understand what are the abiological processes, what are the biological processes, was a controversial topic. Can someone weigh in on that? Yeah, Steely. Because to me it seems so obvious. Like obviously we should be trying to figure out what's happening in the system.
Yeah, I mean, a lot of this spans out of the initial Alan Hills debate back in '96, where the whole debate about whether or not there was life on Mars and how you would go about detecting it. And it really is, that became a hugely controversial. Oh, a bit of feedback. Yeah. Yeah, babe. No, it's not good. And anyway, so that sort of did kind of, that's how that started out. And the interesting thing about that is that Alan Hills meteorite was contaminated with Earth bacteria. And all the techniques said there was no life there. And that's really what started it. It's like, you can't find Earth life in a rock on Earth. How are you going to find life on Mars when it might not even resemble Earth life? So 25 years later, we know that Alan Hills organics were produced by serpentinization reactions, that Mars has undertaken abiotic chemistry, that the stuff we find in meteorites has been verified on Mars by Curiosity and by Perseverance. So it doesn't, we're quite happy with that. We know what's in carbonaceous chondrites. Most carbonaceous chondrites are contaminated by Earth life as well, by the way. It's fungi and bacteria all the way through those things. So we have to separate those things out. But for a while there, it was really contentious. And if you actually look, nothing celebrates the McKay team or the Gil Levin team, and that's another debate. But they're the only people who made these claims that really stuck and advanced the field. So it was really contentious at the time, back in 97, 98, 99, especially with the Alan Hills debate at that point. And then back in the 70s with Gil and the whole discussion about whether or not C-14 release was life in the Viking missions. And he said, well, there's no organics there. But there was chloromethane. But the chloromethane was from cleaning products. But none of the cleaning products contained chloromethane. But, right, so it was really very big controversial arguments at those times.
Well, it sounds like the controversy was trying to make sense of the data, but from Barbara's talk, it also sounded like there was pushback even on the idea of there being an abiotic
Here,
baseline.
yes. Yeah, on Earth, it was the opposite problem. Barbara had a huge trouble getting people to understand that abiotic reactions happen on Earth, and they weren't a consequence of just biota. So on Mars, we had the opposite problem.
Yeah.
So when you look at it, it's planetary or body dependent as to whether or not abiosis is in or biosis is in. And so over time, they're taking that apart. Barbara, do you want to? No, you're doing great. So
She's in my car. I'll pick her brain later.
So over
Online question.
yeah. So over time, that controversy has become less and less. I think as people have understood more both the abiotic baseline here and understood the habitability potential of Mars as astrobiology over the last 20 years has matured. It's become more acceptable to think in these terms than it used to be. Tori, do you have any?
No more than you've already suggested.
Okay. I hope that helps.
All right, thanks. Yeah, let's move on to our next portion of this module, where we're going to hear from Gregoire and Alexei, who unfortunately weren't able to join us in person, but they're happily here online with us. And they're going to present about the Astromaterials perspective of the abiotic background. But before, one second, guys, just as a reminder, immediately after this, when we're done, we're going to, Andro is going to lead us over to the one of the other buildings, the Abelson building, and where we'll have our group photo. And then we'll come back here for lunch. So if you want, you can leave your stuff here. If you're not comfortable leaving your stuff, you can take it with you either way, but we're going to go there, for just as fast as we can to take a photo and then come back. Okay. So, all right, Alexei and Gregoire, take it away. And we'll have time for discussion on this topic afterwards too.
So, hello everybody, and welcome to the Astromaterials section of the Abiotic background workshop. So, talking about how the material from space can alter our baseline abiotic background. Next, please. So thankfully, Chris Glan yesterday already touched on most of the notions I wanted to present in this slide, which is about the provenance of materials. Our best proxies for the building blocks of the bodies we're interested in are meteorites, and as for the organic content, carbonaceous chondrites, namely. Different types of chondrites originate from different parts of the protoplanetary disk, and in particular, the carbonaceous chondrite formed behind the gap caused by Jupiter, but they also formed at different times and in different zones, which shaped their content and gave them each their own history. And Greg will take over on that part and describe what we know about the organic content of these building blocks.
Yeah, so next slide, please. Okay, thank you. Yeah, so as Alexis said, so these meteorites are very important to understand the origin of the organics that can be accreted for the formation of these bodies, but they are also really interesting in primitive chemistry because they give a direct windows of the type of organics that were present at the time of the primitive Earth. So it's really relevant to try to understand what sort of organics can be delivered by these objects. So of course you have different type of meteorites. So today we will focus on carbonaceous chondrite meteorites. That next slide, please. That have a certain content of of organic matter. So they have between 0.1% to 5% of their weight as carbon. And you have two different fractions, soluble fraction, which is represent a quarter of the carbon contents, and the other part which is insoluble. Can you slide, please? Okay, so the first part of this presentation is to give you information about the molecular content of the soluble organic fraction. So we call soluble organic fraction because you can use different solvent and recover this fraction with a solvent, which is not the case for the insoluble fraction. So here you have the data that was obtained by Philip Schmidt-Kopin in 2010 by analyzing this methanol recovery of the soluble organic matter by high-resolution mass spectroscopy. So here you have a zoom on the mass spectrum here, and which is important here to understand is that with that sort of analytical system, you are able to identify ions and to obtain the chemical formula for each ion. And as you can see here, for low resolution mass spectroscopy, you should obtain only one peak. And because of the high resolution, you can have a very interesting information about the molecular diversity that you have here. And what you observe, you have more than 14,000 different ions that were observed. And what we demonstrate is that for each ion that you have here observed, you have up to 30 different isomers. That means different configuration of the atom in the space. So you can see that you have a very, very important molecular diversity that is present in that sort of object. So here this is a Murchison meteorite. And so this is the interest to have this global analysis of the matter that give you a picture of the molecular diversity that you have in that sort of system. And if you look to the different samples that you can have on Earth, you do not find this huge diversity that is observed in this meteorites. So next slide. So next to this global analysis, you can also target to specific compounds. So of course, when you have thousands of different molecules, you will not try to identify each molecule. So you target some specific molecules, and mainly building blocks were searched for. So building blocks that are interested for periodic chemistry. So in that sort of meteorites, you can find sugars, you can find nucleobases, so that are relevant for the formation of DNA or RNA. And you can also find amino acids. So as you maybe know that in biology on Earth, you have around 20 different amino acids. If you look to the Murchison meteorite, you have up to 90 different amino acids. So that show you that there is a non-selected pathway for the chemical formation. That's the difference of biotic system. And which is interesting that in some of these meteorites for amino acids, you also observe the presence of enantiomeric excels in the L form, so up to 20% on isovalene. So you have higher enantiomeric excess for other amino acids, but there are still debates about the possible contamination of biotic origin. So which is interesting here is that you have probably an abiotic pathway that leads to the formation of this enantiomeric excess, and you have scenarios that present the possibility that this enantiomeric excess were delivered at the surface of the Earth and lead maybe to the emergence of the homochirality that is observed in some protein on biochemical system. So that show you that in this soluble organic matter, this soluble organic fraction, you have a very important molecular diversity, and you have a huge reservoir of organic matter that can be available in different planets of satellites. So you can move to the next slide. And so, as I told you, next to this soluble organic matter, you have an insoluble fraction. So it's mainly represented as a macromolecules interaction between macromolecules. So we name that insoluble organic matter because you cannot recover this fraction by any solvent. So you have to apply different strong chemical process to extract this fraction of organic matter. And this is an aggregate of different macromolecules. So you can see that you have aromatic rings that are linked by aliphatic bridge in which you have heteroatoms. So you have these macromolecules, and what we also demonstrate is that on these macromolecules you can have interaction with smaller ones, and this make this insoluble organic matter. So You have some experiments that were performed with Pizzarello. So she takes this inorganic fraction, since insoluble organic fraction, excuse me, and he puts it in a hydrothermal condition. And what they observe is it can release interesting molecules such as fatty acids that can be released in the environment. So often we think that this insoluble fraction is not interesting for instance, probability chemistry, but depending on the condition in which it will be delivered, you can use it to obtain interesting molecules that can be used then for chemical evolution. So you can go to next slide. Okay, so then the main problem, and it was discussed just before in the question or during the previous talks, is that when you take a meteorite on Earth, you can have contamination. And this is the main problem, for instance, for the determination of the presence of enantiomeric excess for amino acids. So you have two space missions that go to a specific asteroid to recover the sample of their surface and to send back the samples to Earth to make the same analysis that we can perform on Earth, and that was performed on Earth for meteorites, excuse me. So you have the Hayabusa mission 2 that go to Ryugu, and you have the OSIRIS-Rex missions that go to Bennu. So next slide. So here is just to show you an example again of a global analysis of the soluble organic matter that was observed in this sample. So at the right, you see the signals that we obtained with Murchison. So here again, this is obtained by high resolution mass spectroscopy. And as I told you, for each ion, we can have the stoichiometric formula. So here, this is a representation of the ratio between He, OC. And which is interesting here is to see the repartition, the space of the ions that are observed. And so you can clearly see that you have some similarities between Bennu and Ryugu. And if you go to Murchison, you see that you can increase the oxygen content relative to the carbon. That means that you have more oxidized forms. And if you see to the different groups, CHO, CHNO that are observed, you have much more molecular diversity observed in Murchison compared to the both asteroids. Which is also interesting. If you compare the both asteroids, you can see that you have a different repartition between the chemical groups. So for instance, you can see that for Bennu, you have much more nitrogen groups than for Ryugu that have more sulfur groups. That means that you have probably, we start to see that we have probably a different chemistry that occur and that lead to the samples that were recovered from the surface of the asteroid. So that why, in the conclusion here, is that in fact the Bennu sample presents a higher nitrogen chemistry than the Ryugu sample, while Ryugu samples have got higher sulfur chemistry than the Bennu samples. You can go to the other slides. So here again, we can target from specific molecules. So again, the same that were searched for in meteorites. And so we also identify amino acids. So you have roughly the same amount of amino acid between Bennu and Ryugu. But which is interesting again here is that even by looking on targeted molecules, you see differences. For instance, in Bennu, you have much more higher concentration of pyridines than in Ryugu, and inversely, you have more purine nucleobases. And this is interesting because the chemical pathways that lead to these different molecules are different. That means that you have a different history that occur in these two asteroids and barren bodies of this asteroid. And the other point also is that when you look to specific chemical functions, such as carboxylic acid or amines, you also see a difference that clearly demonstrates that these two objects undergo different evolution, different physical evolution, geochemical evolution, and chemical evolution. So you can go to the next slide. And here in this slide, so we compared the organic contents, so the bulk of nitrogen and the bulk of carbon in Bennu and Ryugu compared to different class of meteorites. So if you go to the CR, CM, CI meteorites, in fact, you increase the alteration, aqueous alteration of the parent body of the meteorite. And you can see that the Ryugu is really related to Orgueil CI meteorites about the content of carbon and nitrogen. But if you look to the Bennu, clearly you see a huge difference. And next slide, please. And in fact, what's the analysis of the mineralogy and the organic content of these two sample return missions shows that in fact Bennu was submitted to an extent aqueous alteration, but at very low temperatures, and because probably it incorporates a huge amount of ices, while Rigu was submitted to a much higher thermal activity, hydrothermal activity, that could explain the differences that we observed just before, the nitrogen content, and for instance, the sulfur chemistry that was observed in the Rigu samples. So next slide, please. So another point is that, which is, as I told you, which is really important, is that why these sample return missions are very important is that because, again, when they compare Rigu to a CI conduit, so for example, the augers, they clearly demonstrate that in fact, because you can have a very rapid contamination of the meteorites with water or with biological system, you have a modification of the organic content. And for instance, here I just give you an example is that between the interlayer in the mineral phase, they observe the presence of organics in the Rigu samples, while in augers they didn't observe this organics. That means that probably because of the contamination by the Earth environment, you have a modification of the organic content of the meteorite. So clearly, this is really important if we want to really understand the organic composition of this extraterrestrial body. It's important to have this sample return mission because you have a clear example of the organic content that was not contaminated and so altered by the Earth environment, which is really aggressive compared to the organic content of such different molecules. You can move to the next slide. So here I gave you some examples about the history of this asteroid. So which is really important here to understand is that the history that lead to the formation of this object is very complex. So here, if you take the figure, the left figure, so we start by a part of the organic content that could come from the interstellar medium. You have another part which can come from the outer protostellar nebula, and another part that can come from gas phase chemistry. And so you mix all this origin and you have the parent body of the Rigu sample. And then when you have this parent body, you have a new alteration that can lead to the formation of the current organics that are present and observed in this body. And we know that you have aqueous alteration because of the evolution of the mineral phase that lead to the formation of phyllosilicates. So that show you that you have a very complex history that leads to these organic contents. And depending on the place where the parent body was formed, where the planetesimal was formed, you will have a different evolution and different organic contents that you can observe. And this is much more difficult to obtain a really information about this story, because if you take the figure of the right, you see that between two different samples, two different aliquots of the sample return from the Rigu, you can see that you have a different composition in the organics. For example, here you have a glycine and the evolution of glycine and another amino acids. And depending on the ratio, we know that, for instance, one sample was probably originated from interstellar medium, from ice chemistry, while the other one was come from probably from higher temperature environments. So that show you that when we try to understand the origin of these bodies and the origin of its organics is a very complex because you have, you can go to the next slide. Because in fact, you have a very complex evolution of the body in the protosolar nebula, and you have a mixing of the planetesimals, and at the end, you obtain parent body of this object that were subject to very complex origins that mix different evolution of organic matter and mineral matter that can then lead to the formation of the planetesimal. You can go to the next slide. So that's why, in fact, when you go to the different meteorites, you have a huge amounts of possible meteorites. And here we are interested about the carbonaceous meteorites. And again, you see that you have an evolution in these different meteorites depending of their aqueous alteration and thermal alteration. So if you go to CICMCR, this is the parent body where mostly aqueously altered at low temperature. And when you go to the COCV, you increase the temperature of the system, probably because you incorporate much lower amount of ices at the beginning, so you increase the temperature of the system. And so you have all these different possibility of bodies that can go to the formation of your planets or of your Europa, for instance, and that lead to different delivery of organic content. You can go to the next slide. So, okay, so the main problem is that we have different analysis of the mineral phase of these bodies. We have the organic matter also that can give information about their possible origin. But the main problem here is that we do not know exactly the evolution. So that's why we can also develop experiments in the lab that will help to obtain information about the origin of these different objects. So you can go to the next slide. So here, this is one system that will develop in the labs that will allow to understand what sort of chemical evolution we can obtain when we start from interstellar medium up to the formation of the protonebular system, and then that can evolve to the formation of asteroid and what sort of asteroid what sort of evolution we can have in asteroids. So next slide, please. So the first step that I will show you, so we start by the formation of ices as they are observed in interstellar medium, and we'll submit them to energetic processing, electron, UV, or ions, and then we warm the system. We'll try to understand what sort of organics that are in the gas phase and what sort of organics that can remain at the surface of interstellar grain in the protosolar nebula. Next slide, please. So if you look to the gas phase, so if we start from an ice of water, methanol, ammonia, so which is deposited at low temperature, 20 K, you submit to UV, and then you warm the system up to 300 Kelvin. You can recover different molecules, and what you observe is that even if you start from only one source of carbon, which is methanol, you can observe in the gas phase a huge molecular diversity. Here you have 40 different molecules that were observed, and you have all the chemical functions that you can obtain from methanol, but you have also amine, nitriles that were also found. So I show you that by starting from this very small ices with a low molecular diversity, you can generate a very important molecular diversity. And if you compare to what is observed in comets, next slide, you can see that in comets, you can also have this molecular diversity. And that means that probably that sort of diversity that is observed in gas phase can be generated through the processing of ices that you have at the surface or in the core of this body. Next slide. So the next question is, so we observe that from ices we can generate an important organic diversity, and now it's a question, is it possible to obtain the same molecular diversity in the solid phase? Next slide. So we analyze here the residues that were formed from an ice of water, methanol, ammonia, again, UV irradiation at low temperature, 20 Kelvin, low pressure, and then we warm the system up to 300 Kelvin. So we have the desorption of all the volatiles, and we recover what you can see on the left here, a residue, which is an organic oil, in fact. And at the right, you have infrared spectroscopy of the residue. You see that we have different chemical function. We can observe different molecules, such as hexamethylentretamine, for instance. But if we want to have a higher information about the molecular diversity that was generated from this ice, we need again to use what was used to analyze the organic content of meteorites, so high resolution mass spectroscopy. So next slide. And when we recover this residue and we analyze them with this technique, you can see that we have again thousands of different molecules that were observed. So you start only from water, methanol, ammonia, you submit to UV. Next slide, please. you warmed up to room temperature, and in fact, you observe thousands of different molecules. So here you have more than 14,000 different ions that were observed, up to macromolecules that present 4,000 Dalton as mass. So that shows you that from these very ICs that are very, as a chemist, very small molecules, you are able to generate, because you put energy in the system with UV or electron, you generate a complex and rich chemistry that will lead to this important molecular diversity. So we can also target to specific molecules in this residue. Next slide. And we also observe nucleobases, sugars, dipeptide, amino acids. So you can see that if we go back to what we observe in meteorites, we have some similarities that are observed in these synthetic samples that were generated in the lab from analogs of interstellar ices. So this is really interesting to maybe obtain information about the possible origin of fraction of the meteorites that are observed in, of the organics that are observed in meteorites. Next slide, please. So then to finish, so okay, we form organic matter in the lab, so this is synthetic, and we have from this ices, water, methanol, ammonia, we form soluble organic matter, and the question is that then, is it possible to form insoluble organic matter? And so for that, you take this soluble organic matter, you submit it to high energy processing, and then when you compare what you have before and after the energetic processing, you see that you have a modification of the organic content. And in fact, you generate an insoluble fraction. Now the question is that, is it these synthetic samples are really relevant to obtain information about the chemical evolutions that lead to organics that are present in meteorites? Next slide. And if you compare to what is observed with this exactly same analytical method to the IOM of Paris meteorite, for instance, you see that you can have some similarities in the molecular distribution. So here I do not say that we form the insoluble fractions that we have in Paris, but we have something that presents similarities. But if you look to the soluble organic matter, clearly you have a sample which is totally different. So that means that, next slide, please. We miss probably a part of the process, and this is because what I show you here, we only simulate the first step of evolutions that lead to the organic contents of soluble and insoluble organic matter that can be present in the solar nebula or protoparietal disk. But then you have an accretion step that lead to the formation of asteroids. And what we know from the observation of meteorites, we know that we can have secondary alteration and probably aqueous alteration in the parent body of meteorite. So that's why next slide, we make a new experiment where we take this soluble organic matter generated from our ices and we put it in the simulated condition of asteroid processing in water. Next slide. And what we observed is that we have a total evolution of the molecular diversity. So here you have before alteration, after alteration. So we keep the molecular diversity. You have still thousands of different molecules, but we clearly modify the organic contents of the molecules. And which is interesting is that if you compare to meteorites, next slide, please. So here you have the soluble organic matter of the Murchison meteorite, so that is superimposed to what we observe in the residue. You clearly see a huge difference, and you are much less oxidized. And next slide. If you compare to what is obtained after hydrothermal alteration, you see that we have a system that presents much more similarities to what is observed in Murchison. So here again, I do not say that we form what we have in meteorites, but next slide. But what we demonstrate, in fact, is that we are able to simulate in the lab an hypothesis that allow to the formation of organics that are observed in Rigu sample, for instance. And we demonstrate that if you start from an interstellar ices, you can generate different huge molecular diversity, and then you have a second evolution in the parent body of this system. So in conclusion, we can see that when you look to these different samples, we have a very important molecular diversity which is formed, and you have soluble and insoluble organic matter. And there is an important organic heterogeneity between objects, but also inside the same object. And this is because of a very complex history of formation for these different molecules. So now I leave Alexis to continue the presentation.
Thank you. So once the matter has gone through this tortuous process and makes its way into forming a planetary system, such as the one of Jupiter or Saturn, the story is not over. There are still many things that can happen that will shape it and that will redistribute it. And some elements in the planetary system we know show that we can expect some very different history. A tracer of that is, for example, that the Galilean moons have a monotonous density gradient decreasing with distance to Jupiter. The stark contrast in water-rock ratio between Ganymede and Callisto, that was pretty much 50-50, to Io, that is dry, and Europa, that has only around 7-8% water. Saturn's moon have a gradient in radius up to Titan, but an irregular density, which shows a more tortuous process. And the Uranian moon also have a monotonous density gradient, but the other way around. So whatever decided the repartition of volatiles to refractories also probably has implications for organic content. And recent studies using the density and moment of inertia of these bodies and an additional layer of modeling calls from a high complex organic matter fraction in many of these bodies, up to 30% for some of them. It's a model, a very interesting and provocative one that should reassure us about how much carbon we have to play with. And the processing of this matter will depend on the scenario of formation and on the history post-accretion. And it's going to affect complex refractory organics, but also volatile organics. Next slide, please. So a little zoom about on the Jovian system. The scenarios can fall into families of dense and hot models or cold and starved model, which of course has implications as to what will happen to the organic matter. So it's out of the scope of this talk to do a full view of the debate around the formations of Galilean moons, but I want to illustrate two recent scenarios that for Europa have vastly different implications, and both aim at explaining where does Europa's little water come from. One scenario on the left, so the Mousis et al. Scenario of 2023, it would be the formation of the Galilean moons through dehydration of CM-like material, so dehydration of phyllosilicates that would come without ice into the system. And the ice content of Ganymede and Callisto would come from the condensation of this lost water into the beyond the snow line, so the limit at which you can condensate water back where it's cold enough, while Europa will owe what little water it has from dehydration of its of the silicates that formed it. Another scenario with a much colder history, that's the Petrica et al. Scenario, would involve a CV meteorite base, so a much more thermally processed meteorites with a much lower fraction of organics, and that would come with very, very little water. And the water and a lot of organic matter would come from ulterior cometary input. So we're talking about pretty different materials here. Next slide, please. Meanwhile, the Saturn and Uranian system call for probably some some very dramatic events with some of the scenarios involving, for Saturn, formation of moons from a massive ring that would be the result of a Titan-like moon disruption, in which the heavier core would have been lost to Saturn. So that involves redistribution of matter from large bodies that had their own history. And for Uranus, The system would be resulting from a collision involving a large rocky planet. That's not the only scenario, but that's one of the most popular ones. And the increasing density would be explained by Rayleigh distillation during the formation. Well, I would love to see a modeling like that would not only work on refractory minerals versus ice, but also for various organics. Next slide, please. So in the end, we are left with uncertainties on the source of the materials, CI versus CV, which is different organic matter in different quantities, or inputs from comets. And well, we're still lacking a lab sample of refractory organic matter from comets. So we do benefit a lot from insights from Rosetta or from IDPs. We would then have, depending on the history of the circumplanetary disk, the effect of a snow line. And to illustrate the power of snow lines, I'm showing it at the scale of the solar system, how the fact that each volatile has snow line would play on the C/O ratio. And an example of the effect of snow lines, it would be the peculiar composition of comet C 2016 R2 pan-stars, which is exceptionally rich in CO, which is also a reminder that between comets, we may see some pretty large differences. And then there's the post-accretion evolution that could induce a cooking of organic matter. Extraction of soluble organic matter, hydrothermal processing, all of that has been covered, and it's something that is that's motivated a lot of work and still does, thankfully. But there's a bit of a dearth of data on IOM transformation at very high temperature, because it doesn't apparently just graphitize. Next slide, please. And once you have formed your body with its population, well then, it doesn't stop. You have a constant exogenous inputs. The first one I'm going to talk about is micrometeorites and interplanetary dust particles, which represent a non-negligible flux, maybe not at the scale of the total content, but that flux happens to be hitting the part of the body that we can access. Due to the influence of Jupiter, in the case of the Jovian system, the flux is more homogeneous than one would expect, and it has the very beneficial effect for us to cause an ejected halo of material around the Galilean moons, and that was shown by the Galileo mission, and that is something instruments like SUDA on Europa Clipper are counting on to give us great insights about the composition of the surface, that we can access these particles from close orbit. At the level of Jupiter, interplanetary dust particles are dominated by Jupiter family dust comet, by the Jupiter family comet dust, which is a great thing because that's the one we know quite a bit about, thanks to how accessible it is from near Earth orbit, and thanks to Rosetta. And it's rich in organics and should be expected to be consistent with 67P. Other giant planets see a bigger influx of other particles that we know a bit less about. And one should not forget the importance of intrasystem dust exchanges, illustrated in particular by Iapetus and its very dark hemisphere due to dust bombardment coming from outside in the Saturn system, namely mostly Rhea. Next slide, please. Larger impacts has a physical effect of impact gardening that homogenizes the upper layers. When Kevin the other day was giving the figure of 10 centimeters on which we would have to dig to find some not too irradiated material, well, that figure also include homogenization due to impact gardening. But also, macro impacts would be a proposed source of water organics. I've already touched on that as an explanation for Europa's hydrosphere. So that would involve some pretty large amount of carbon delivered to Europa. Prebiotic molecules can survive some large impacts that has been studied. And not only that, but impact can participate in forming complex organics that, by shock synthesis that could form amino acids. So that's another contribution to the abiotic background that you can expect post-formation of a body. Next slide, please. Another contribution is energetic particles. So one would think that the solar wind, which is the first you would think of, that with 95% proton and only 1% of anything heavier than helium, that you wouldn't see much of an evolution in the elemental composition. And it's true that physicochemical effects are extremely relevant and cause visible alteration on the surface, again, the part that we can access. But we did some experiments with sulfur implantation that was consistent with a few 100 million years out there in the solar system. And we did end up with detectable sulfur-bearing compounds only from the sulfur that was implanted with solar wind-like doses. But of course, as far as energetic particle goes, the best, or rather, I should say, worst place to be in the solar system is the Jovian magnetosphere. It's internally driven, so most of the ions come from inside. And Jupiter's magnetosphere is especially dense with large amount of hydrogen, oxygen, and sulfur ions, sulfur and oxygen being courtesy of Io's volcanism. Next slide, please. And what these energetic particles do, well, first, they participate in the formation of exosphere by sputtering, with the contribution of electrons have been revised up recently. They can even cause potential energetic desorption of large molecules, which would be great as far as observation go, but as far as I know, hasn't been modeled precisely for the specific context of icy moons. And it causes fast destruction of organics on the surface. Down there, you can see a typical infrared spectra for a typical experiment of destruction of propane in water under electron irradiation. And you see the features of around 2,800 centimeters -1. Sorry, around 3.4 microns. You can see the quick disappearance of the propane CH features, while in the middle, you can see the birth of CO2. And when you look in the infrared, the most effect you would see usually is the formation of what I call the usual suspects of irradiation of organics in ice, CO2, CO, CH4. But since we're flying these fancy mass spectrometers now, we are interested in the most complex and minority products. There is whole galore of products that Greg already hinted at. And you know it can be pretty complicated because on the left, you see the processes that happen just when you irradiate pure water. That was just to drive home the possible complexity. Next slide, please. So this is the result of irradiation of pure methanol in Europa-like conditions, so 50 to 130 K, and the GCMS results of the volatile phase that we captured at the end of the experiment. So Greg already explained the methods. So that was us dipping our tools into electron irradiation. And we see an interesting diversity of products and especially of families, which, and that sends us back to Jeff's presentation, with some products that could be normally used as diagnosis of hydrothermal conditions, in particular the framework proposed by the Kirt-Robinson publication in 2023. The alkene to alcohol ratio could be an interesting indicator of temperatures. Well, here we started with pure alcohol, and we end up with some alkenes in quantities that, transposed to the Robinson framework, would seem to indicate a very hot hydrothermal fluid. Well, no hydrothermal fluid was involved in the making of this cocktail of organics. Next slide, please. The proportion between organic families indicate that our products are dominated by aldehyde and ethers. And as temperature changes, we do change the proportion between the products, but overall the background is relatively consistent. It's not as if one family completely disappears if you change the temperature. And I want to stress that this was obtained at a relatively low dose of electrons that is much lower than geological times on Europa. So we're talking at most a few hundred years if you go to the less irradiated parts of Europa's surface. So very early, we can end up breaking the geothermometer just through irradiation. Next slide, please. And so that was volatile stuff, but now a word on refractory residues made with Europa in mind. So on the left, this monstrosity is a residue of pure propanol irradiated with sulfur ions. I'm sorry for how Google Drive messed up the formatting compared to the original. And on the right, we see published results of the analysis of a residue made with water plus propane irradiated with sulfur ions again. The figure shows the number of carbons by a molecule versus double bond equivalent, and in a insoluble phase and soluble phase, because yes, we get both. And we see that we have included a lot of the oxygen of water into the residue, and that we do get to see a few sulfur-bearing species. Next slide, please. So in itself, this data is not super interesting if you don't compare it to to what you get with other precursors. So how well can we play the game of guess the precursors? Well, on the left, you have residue made of water plus propane. So with CHO in blue, CH in gray, and CHS in green. In the middle, water plus propanol, and on the right, pure methanol. And if you're asking where is the water plus methanol, well, it didn't produce enough residue to get a clear signal. And between the two on the left, the issue is that you don't really see a great way to distinguish them. You end up with something that is pretty hard to diagnose, pretty hard to go back into what was before. And pure methanol shows some hope that we are a bit closer to the original O2C ratio. But some preliminary results I got with pure propanol, with propanol plus and more propanol plus water indicates that this may not be that easy. Next slide, please. And how does it relate to what has been observed? Well, with Europa, that's pretty fast. Yes, the hemispheric dichotomy of Europa really fits the inferred flux of heavy ions, so that's great. But as far as organics go, observations so far do not show any organic species on the surface of Europa. The only carbon bearing that we know is there is CO2. And CO2 could be considered a smoking gun for irradiation of organics on an ice surface if we exclude all the other explanations, such as endogenic source, which we just can't. In the case of Ganymede, organics have been detected by Juno with potentially aliphatic aldehydes. Remember how aldehydes were a big chunk of our products in our experiment? And another pretty clear case is Caron's residue explained by UV processed methane. But this is a UV we're talking about here. So next slide, please. So in conclusion and way forward, so the formation of complex organic matter, including prebiotic molecules, occurs very early in the building blocks of planetary bodies. Body history is key to these matter's properties. And large organic diversity is not yet fully understood at all stages of the formation. And yes, I say bring back a comet sample. Sorry, Sarah, I'm not saying that I would have preferred Caesar instead of Dragonfly, but actually I would have wanted both. Inputs of organic matter and processing is still an ongoing process. But thankfully, we have instruments on board of, for example, Clipper to help us deal with exactly that. Some knowledge gaps, well, I'm belaboring the point of refractory matter in comets, of radiation chemistry of complex mixtures, because so far the mixtures that have been done are usually limited to some organics plus some volatile stuff, well, water, of course, but also ammonia. But inclusion of inorganic species of salts is quite more challenging. And so unknown information scenarios mean that astrobiology just cannot be dissociated from planetary science in general and from the study of planetary origins. Thank you for your attention.
All right, excuse me, thank you both. Yeah, so we have time for questions for Alexei and Gregoire.
Hi, this is Ashley Hanna from the University of Maryland. This is a great talk. I actually was really interested in the diversity of organics that you guys have found, and this also can go to Heather as well. But I was wondering, with the diversity, how with the high resolution, excuse me, mass spectrometry, is there any plans or have there been any studies of putting some of those samples returned onto engineering testing units for mass spectrometers that are flying for other missions, just to understand how well current spaceflight mass spectrometers can characterize the organic matter, even though it's a shorter mass range?
Yeah, I think this is maybe Alexei, you can discuss about your project because this is one of the aim. Yeah, clearly the point is that we use high resolution mass spectrometry to obtain this information of the molecular diversity, and then is to confront this molecular diversity to confront spacecraft and mass spectrometers that will be on board of the spacecraft to this molecular diversity, and to see what sort of information we can obtain from this system. And clearly we will lose information, but then we will try to understand what sort of specific signature we observe on mass spectrometers that will be on board of this spacecraft that could be linked to specific organic origins. But yeah, the best is to develop high resolution mass spectrometers that can be fly. So you know that you have CNES and NASA that work on the Orbitrap development for that. But if you want, I think obtain information about the possible biotic presence on an object, you need to have this high resolution, because otherwise, which is really important to understand, is that if you look to an abiotic environment, okay, some we can discuss in detail, but generally you will generate a very high resolution, molecular diversity, because the chemistry is not selective. Okay, which is different from biotic systems. So you need to have this information of the diversity that is present in the environments. And if you see that in some environments, you do not see this molecular diversity, then maybe you can think that maybe because this is the environment that's for example, if you have a lot of oxygen, you will degrade the organic chemistry, so you will limit the molecular diversity, but you can directly have an information on that. But it can be also related maybe to the presence of specific chemistry, and maybe that selects pathway and that reduce the molecular diversity. So I think this is really important to have such a system that can be developed for space mission. Alexei,
and yeah, one thing I might add is, so I have a project that just started that includes a later phase in which we will process some of our mass spectrometry data to turn it into something akin to what mass specs would see. So basically reshaping the spectra to fit what mass specs, so the mass spectrometer of your Clipper would see with its capabilities. So I know the SUDA team with the little bit setup in Berlin has been working on, I would say, more and more complicated grains. And we've done a proof of concept where one of these water, methanol, ammonia residues was passed into a little bit. So that is an area with a lot of interest. And I think the teams, well, there are members of these teams in the room, so they can say it much better than me, but they do get how critical it is to worry about this super complex organic matter that can be generated in the lab.
Thank you.
Shannon McKenzie, APL. Thanks for these talks. I think my question might be better directed at Frank as a follow-on to what Alexis was just saying. Is SUDA planning on measuring some of the like inner dust particles in the system, or just during the Europa closest flybys?
No, actually, this is even made it in the STM that SUDA
Wow.
monitors the external infall onto Europa, and with that you have to monitor basically everything that swirls around in the Jovian system, mostly originating from Io, but also exogenous sources will be monitored. Yeah, that's part of the job.
Cool. Thank you.
Yep. Tori Holler from NASA Ames. Thank you both for the excellent talk. So this is a question about the isoradiation experiments, which have always fascinated me, because it seems like what you get is the result of sort of very high energy combinatorial processes, and that's cool from a chemical diversity standpoint, because it seems you can get almost anything you want. It's scary in the context of this workshop because you can get almost anything you want, and it's also scary in that the outcome seems a little bit less determined or predictable. And so the question is this: very often I hear these experiments couched in terms of, you know, we were able to make this, we found that. If you consider that, I'm going to try walking to the back. If you consider the outcome of these experiments as a set of compounds, rather than in terms of individual compounds, is there something about
Sorry, I thought I turned that off.
Yes. There we go. That's better.
My bad.
So if you look at the outcomes of these experiments, not in terms of individual compounds, but as a set of compounds or bulk properties of the compounds, is there something about those outcomes that still makes them appear like the result of clearly abiotic processes? Are they still distinguishable, or can you get as many outcomes as you apply input conditions?
So yeah, maybe I should have shown a raw spectrum, because when you look at the entire distribution, well, you do see a clear abiotic distribution. You see that there hasn't been much selection in the process. And yes, you can always say we obtained this, we obtained that, because we obtained such a high diversity, but we clearly don't have a selection behind it. That's the danger of doing a targeted analysis looking for a specific compound, that yes, you may have a chance to find it, but it's very important to look at the whole of the population you are getting, and it will show, I think, a bit clearer as a result of an abiotic process, rather than giving any false alarm. I don't know, Greg, if you want to add something on that.
Yeah, no, I think, but I think, yeah, if you target on different, you can see that from, for example, for amino acids, okay, as you said, from the ice chemistry, in fact, because when you irradiate your molecules, you form radicals, and because you have radicals, you have very low or no energy barrier, and that means that you have all the chemical space that is open to you. So that's why you have this so much this high molecular diversity. And if you look to specific chemical families, in fact, you will find again this molecular diversity. Okay, when you look, for example, for fatty acids, if you compare biotic samples to what we form in the lab, or in what you have in meteorites or asteroids, you clearly see a huge difference. Okay, you clearly see that you have a very important selectivity on Earth if you look to the biomass or in the biotic system. And the problem is that because of the history of the Earth, you know, that you have a huge processing, and now the life totally modifies the organic content of the initial primitive Earth. But if you look to a systems, for instance, if you have biochemical systems that do not contaminate all the system. We have a merging between abiotic molecular diversity and the biotic signature, and this is which is really difficult then to decipher what sort of analytical strategy we have to develop to identify a biosignature in this biotic system. It's a very, very difficult question, okay? Because in fact, we do not have, I think, the technology that is on board of spacecraft to obtain this information currently. So that's why sample return mission are very, very interesting missions. So I know that it's very complex when you go to the outer solar system. I'm not in that sort of question, but clearly when you see what we can obtain from asteroid Ryugu and Bennu's information that we can obtain, and the difference that you obtain in the organic content between meteorites and these samples, you clearly demonstrate that this is really important to have that sort of mission, to clearly to maybe have a possibility to obtain information about the possible presence of biotic traces and so on.
Any last burning question? All right, well, I think we're gonna cut it off there then. And let's thank Greg and Alex one more time. All right, so that brings us to the end of the morning portion. As I said before, we're going to now go take a photo, and then we'll come right back here to have lunch in the place where we've been having all our meals. And we're gonna start the afternoon talks right at 1 o'clock. For those of you online, that's an hour and about 25 minutes from now. Actually, Laura, did you want to say something? We wanted to ask you if you wanted to announce your database.
Hopefully, I don't know if everyone can hear me. NASA, thank you. So NASA is funding the development of the astrobiology spectral database, which the whole idea is that it's going to serve as a repository for experimental data of abiotic organics generated in the lab or extracted from Astromaterials. This is something I think that's really important for the community because we don't actually have a great place to put all of that data. And it's also really important because abiotic organic chemistry, as you're hearing, is very complex, and there's just no way any study can actually describe all of the organics that are being generated. We lack commercial standards for a lot of things, and so we really want to preserve that data for future context of future sample return missions and whatnot. And so I have a couple of business cards out on the table as well as in front of my poster and on me as well. We have a workshop in July, so I would love if all of you could participate, or I have a survey that would be great if everyone here could participate in. It should take less than 10 minutes. And yeah, thank you all for your attention.